Level 1. Counting stones and tallies. The simplest form of computing was keeping count with stones, bones or marks on sticks. This practice dates back at least 40,000 years. The Ishango bone found near the Nile shows notches carved in deliberate groupings, likely used to record numbers or even simple multiplication. In Europe, tally sticks were used for centuries in trade and taxation, with each notch representing debts owed or payments made. The system was crude, but it showed a critical step in human thought, the ability to represent quantities outside the human mind. Instead of just remembering how many sheep were in the field, a person could mark it down, offloading memory to a physical object. This shift from memory to record keeping was the seed of computing. Level 2. Egyptian and Babylonian number systems. By 2000 BC, civilizations like the Babylonians and Egyptians had developed structured number systems. The Babylonians used a base 60 system, which still survives in how we measure time into 60 minutes and angles into 360 degrees. Their system made astronomical calculations possible, allowing them to chart the stars and predict eclipses. The Egyptians used a decimal system with hieroglyphs for powers of 10. This made construction projects like the pyramids manageable, as workers could measure distances and calculate volumes with consistency. Without a reliable number system, large-scale engineering and science would have been impossible. These systems laid the groundwork for all later mathematics and computation. Level 3. The abacus. The abacus emerged around 2300 BC in Mesopotamia and later became refined in China, Japan, and Rome. It used rows of beads sliding along rods or wires, each representing different place values. Merchants in busy markets could perform addition, subtraction, and multiplication faster than by writing. A Chinese merchant could tally profits or calculate exchange rates in real time while dealing with customers. Even into the 20th century, a skilled abacus user could outpace early electronic calculators. The abacus trained generations of people to think about numbers structurally. It was not just a tool, it was an early computer in human hands, showing that mechanical processes could extend mental capacity. Level 4. Roman numerals and their limits. Roman numerals dominated Europe for centuries. I for 1, V for 5, X for 10, and so on. They were useful for counting soldiers, taxes, and trade, but they were terrible for mathematics. Try multiplying 47 by 13 using Roman numerals, and you will quickly see the inefficiency. Without a place value system or zero, complex calculations were nearly impossible. This meant that advanced commerce, banking, and science were slowed. Yet Roman numerals still appear today, carved into monuments, clock faces, and book titles. They remind us of how far number systems have come, and how much human progress depends on the efficiency of notation. Level 5. Greek geometry and algorithms. Around 300 BC, the mathematician Euclid wrote the Elements, a systematic collection of geometric principles. His method was step by step. Start with axioms, apply logical rules, and arrive at a solution. This was one of the earliest examples of algorithms. Algorithms are the backbone of computing, and Euclid's work showed that problems could be solved not by intuition alone, but by process. Greek geometry was not abstract. It guided architecture, engineering, and astronomy. For example, using Euclidean geometry, builders could calculate the height of a distant structure by measuring its shadow. This systematic thinking was an early sign of computing logic in action. Level 6. The Chinese suanpan. While the abacus existed in multiple cultures, the Chinese perfected it around the 2nd century BC with the suanpan. Its design allowed users to calculate using both decimal and hexadecimal systems. Traders in markets used it for everyday transactions, while scholars used it for advanced calculations in astronomy and engineering. In the Ming dynasty, officials tested civil servants on abacus skills as part of their examinations. Even in the 20th century, abacus masters could compete with modern calculators. A famous contest in 1946 saw a Japanese abacus user beat an American soldier armed with a mechanical calculator in both speed and accuracy. This tool proved that human skill combined with mechanical aids could rival or surpass machines. Level 7. The invention of zero. The invention of zero in India around the 5th century was a silent revolution. Earlier number systems had symbols for values, but no placeholder for nothing. Zero made the place value system work, allowing compact representation of large numbers. With zero, writing 1005 required only 4 symbols instead of a string of Roman numerals. This efficiency supercharged arithmetic, making multiplication and division manageable. Zero also carried philosophical weight, symbolizing the concept of nothingness. It spread from India to the Islamic world and then to Europe, transforming mathematics. Without zero, algebra, calculus, and computing as we know it would not exist. Level 8. The Islamic Golden Age and Al-Khwarizmi. In the 9th century, Baghdad's House of Wisdom became a hub for knowledge. Scholars translated works from Greece, India, and Persia, preserving and expanding them. Among them was Al-Khwarizmi, whose writings on algebra and systematic problem-solving laid the groundwork for algorithms. His very name gave us the term algorithm. Al-Khwarizmi introduced Hindu-Arabic numerals to the Islamic world and eventually to Europe, replacing clumsy Roman numerals. His work allowed commerce, astronomy, and engineering to advance with more efficient methods. For example, merchants could calculate complex interest and astronomers could map the heavens with greater precision. This intellectual bridge was essential to Europe's later scientific revolution. Level 9. Mechanical calculators appear. By the 17th century, inventors began building machines that could perform arithmetic automatically. Wilhelm Schickard, a German polymath, created one in 1623 that used gears and wheels to add and subtract. It was lost in a fire, but it marked the dawn of mechanical computing. These machines were expensive and unreliable, but they hinted at what was possible, shifting calculation from human hands to mechanical systems. For example, astronomers in the 1600s struggled with massive amounts of repetitive math for star charts. A mechanical calculator could save them hours or even days of work. It was a small but crucial step toward automation. Level 10. Pascal's calculator and Leibniz's step reckoner. In 1642, Blaise Pascal built a calculator to help his father, a tax collector, add columns of numbers for accounting. The device, known as the Pascaline, could add and subtract reliably. It reduced the drudgery of bookkeeping and showed that machines could serve practical purposes in administration. A few decades later, Gottfried Wilhelm Leibniz expanded on this with the step reckoner, which used a drum mechanism to multiply and divide as well. Leibniz even dreamed of a universal machine that could manipulate symbols according to rules, anticipating modern digital logic. These devices were limited, but they marked the shift from counting tools to true calculating machines. Level 11. Napier's bones and logarithmic tables. In the early 1600s, John Napier, a Scottish mathematician, introduced logarithms. Logarithms transformed multiplication and division into addition and subtraction, which were far simpler to handle. To make this practical, Napier created Napier's bones. a set of numbered rods that let users quickly look up values. Astronomers, navigators, and surveyors adopted logarithmic tables to reduce long, painful calculations. For example, calculating planetary orbits required multiplying large numbers, and using logarithms, astronomers like Kepler could perform in minutes what once took hours. Napier's work represented the first serious attempt to compress mathematical effort into mechanical shortcuts. Level 12, Slide Rules and Portable Computation. Building on Napier's logarithms, William Oughtred invented the slide rule in 1622. This device looked like a ruler with sliding parts marked with logarithmic scales. By lining up the scales, users could multiply, divide, calculate square roots, and even trigonometric functions. For centuries, the slide rule was the engineer's most important tool. It was used to design bridges, ships, and eventually rockets. Even the Apollo missions relied on slide rules as backup calculators. Engineers carried them in their pockets the way we carry smartphones today. The slide rule became a symbol of practical computation, bridging theory with real-world problem-solving. Level 13. The Jacquard loom and punched cards. In 1801, Joseph Marie Jacquard revolutionized the textile industry with his programmable loom. The loom used punched cards with holes to control which threads were raised, allowing complex patterns to be woven automatically. For the first time, a machine followed instructions encoded in a physical medium. This was a direct ancestor of computer programming. A weaver could design intricate fabrics without personally lifting each thread. The Jacquard loom demonstrated that information could control machines, not just guide humans. Charles Babbage would later cite it as an inspiration for his own designs. The idea of software was quietly born on the floor of textile factories. Level 14. Charles Babbage's difference engine. Charles Babbage, an English mathematician, became frustrated with errors in printed mathematical tables. He conceived the difference engine in the 1820s, a massive mechanical device designed to automatically generate accurate tables of logarithms and polynomials. Powered by cranks and gears, it was a vision of automation for science and navigation. Although the full machine was never built in his lifetime due to funding and engineering challenges, later reconstructions proved his design was sound. Babbage showed the world that machines could not just calculate, but also eliminate human error in systematic ways. His ideas pointed directly toward the modern computer. Level 15. Ada Lovelace, the first programmer working with Babbage. Ada Lovelace saw something that even he did not. While Babbage viewed his analytical engine as a machine for number crunching, she realized it could manipulate symbols, not just digits. In 1843, she wrote what is now recognized as the first computer program, an algorithm to compute Bernoulli numbers on Babbage's hypothetical engine. She also speculated that such machines could one day create music or art, foreshadowing modern computing by nearly 2 centuries. While the analytical engine was never built in her lifetime, her notes made her the first person to see the full potential of programmable machines. Level 16. Telegraphs and early information system. The 19th century brought another leap. The telegraph. Samuel Morse and others turned electrical pulses into a communication system that could span continents. Messages that once took weeks by ship could be sent in minutes. This was not computing in the modern sense, but it was information processing at scale. Railroads adopted telegraphs to coordinate schedules and avoid collisions. Governments used them for diplomacy and military strategy. Businesses used them for financial data like stock prices. The telegraph demonstrated that information could move faster than people or goods, laying the foundation for digital communication networks. Level 17. Morse code as proto-digital communication. At the heart of the telegraph was Morse code, a system of dots and dashes representing letters and numbers. This was essentially a binary system, signal or no signal, long or short. Operators converted language into code, transmitted it over wires and decoded it on the other end. This was one of the earliest practical examples of encoding human language into a machine-readable format. A single wire could carry the complexity of entire conversations. Morse code introduced the world to the idea that information could be represented by a finite set of signals, a precursor to the digital world of ones and zeros. Level 18. George Boole and Boolean logic. In the mid-1800s, George Boole published The Laws of Thought, which laid the groundwork for Boolean logic. He proposed that logical statements could be expressed mathematically using true or false values, much like algebra. For example, a statement like A and B could be treated as a rule with clear outcomes. At the time, his work seemed abstract and philosophical, but later it became the backbone of digital circuits. Every modern computer uses Boolean operations to process information. The simple idea that truth can be represented as 1 and falsehood as 0 is what makes digital logic possible. Level 19. Herman Hollerith and punched card data processing. In 1890, the US Census faced a problem. The population had grown so large that hand-counting data would take more than a decade to complete. Herman Hollerith, an American inventor, developed a punched card system where holes represented data like age, sex, or occupation. Machines could read these cards electrically and tally results far faster than human clerks. The census was completed in just 2 years, a staggering improvement. Hollerith's company later became part of IBM, and punched cards became a standard way to store and process data for decades. This was mass data processing before digital computers existed. Level 20. The birth of IBM. In 1911, Hollerith's tabulating machine company merged with others to form the Computing Tabulating Recording Company, later renamed International Business Machines, or IBM. IBM dominated data processing with punched cards and electromechanical tabulators throughout the early 20th century. Companies, governments, and universities relied on IBM machines for payroll, accounting, and statistics. By mid-century, IBM's influence in computing would expand into electronic computers, but even in its early years, IBM symbolized the industrialization of information processing. The company transformed what was once the work of clerks into a machine-driven industry, setting the stage for modern computing corporations. Level 21. Vacuum tubes and their role in switching. By the early 20th century, vacuum tubes changed everything. A vacuum tube could act as a switch, turning electrical signals on and off, or as an amplifier to boost signals. These properties made them the essential building blocks of early electronic computers. Before vacuum tubes, machines relied on gears or relays which were slow and bulky. With tubes, machines could operate at electronic speeds. During World War II, vacuum tubes powered radar systems and early digital circuits. They were fragile, burned out quickly, and produced heat, but they allowed computing to leave the mechanical world behind and enter the electronic age. Level 22. Alan Turing and the Turing machine. In 1936, Alan Turing, a British mathematician, described a theoretical device now called the Turing machine. It was not a physical machine, but a model of computation. The Turing machine used a tape of symbols and a set of rules to read, write, and move along that tape. With this simple design, Turing showed that a machine could perform any calculation as long as it could be broken down into logical steps. This concept laid the foundation for computer science. Every computer today, from your phone to a supercomputer, can be seen as a version of Turing's universal machine. Level 23, World War II, Cryptography, Enigma, Bomb, Colossus. During World War II, computing became a matter of survival. Germany's Enigma machine encrypted military communications, creating codes thought impossible to break. Alan Turing and his team at Bletchley Park developed the bomb, an electromechanical machine that helped crack Enigma's shifting ciphers. Meanwhile, in 1944, the British built Colossus, the first programmable electronic computer to break German Lorenz codes. Colossus used vacuum tubes and processed thousands of characters per second, cutting code-breaking times from weeks to hours. These machines shortened the war, saved countless lives, and proved that electronic computing could handle problems far beyond human capability. Level 24. ENIAC, the first general-purpose electronic computer. After the war, the United States built ENIAC, the electronic numerical integrator and computer. Completed in 1945, it filled an entire room with nearly 18,000 vacuum tubes and weighed 30 tons. ENIAC could perform thousands of calculations per second, a staggering speed at the time. It was first used for ballistic calculations for the US Army, then later for weather prediction, atomic energy research, and more. Programming ENIAC required physically rewiring it by hand, which could take days. Despite this, ENIAC proved that fully electronic general-purpose computing was possible, marking the dawn of modern computing. Level 25. Stored Program Concept, EDVAC, and von Neumann Architecture, ENIAC, had power but lacked flexibility. In 1945, mathematician John von Neumann proposed a revolutionary idea. A computer should store both data and instructions in memory. This was the stored program concept. The design, first implemented in EDVAC, used memory to hold programs, meaning the machine could be reprogrammed by loading new instructions instead of rewiring hardware. This idea, known as the von Neumann architecture, remains the foundation of nearly all modern computers. Your phone, your laptop, and even supercomputers follow this design: a central processor, memory for instructions, and a flow of data between them. Level 26. Transistors replacing vacuum tubes. In 1947, at Bell Labs, John Bardeen, Walter Brattain, and William Shockley invented the transistor. Smaller, faster, and far more reliable than vacuum tubes, transistors transformed electronics. They consumed less power, generated less heat, and lasted longer. Early computers with thousands of vacuum tubes often failed every few hours. With transistors, reliability soared. By the 1950s, transistors began replacing tubes in radios, calculators, and eventually computers. This single invention launched the miniaturization of electronics, leading directly to integrated circuits and microprocessors. Without the transistor, modern computing simply would not exist. Level 27. Mainframes, IBM 701 and UNIVAC. The 1950s were the era of mainframes, massive room-sized computers serving governments, corporations, and research institutions. UNIVAC Y, delivered in 1951, became the first commercially available computer in the United States. IBM entered with the 701, which brought computing into the corporate world. These machines were not for individuals. They processed census data, weather forecasts, bank transactions, and scientific research. They used punch cards for input and produced results on printouts. businesses and governments invested heavily, marking the start of computing as an industry. Mainframes defined computing for the next 2 decades. Level 28. COBOL, Fortran, and the rise of programming languages. In the 1950s, programming a computer meant dealing directly with machine code, strings of ones and zeros, or assembly language, which was slightly more readable. This was inefficient and error-prone. Then came higher-level languages. Fortran, developed at IBM, was designed for scientists and engineers to write formulas easily. COBOL, developed by a team led by Grace Hopper, was meant for business use, with syntax closer to English. These languages allowed more people to write programs without being experts in hardware. They opened the door for computing to spread beyond specialists, into broader use across industries. Level 29. Magnetic core memory. One of the key advances of the 1950s was magnetic core memory. This technology used tiny magnetic rings strung on grids of wires, where the orientation of the magnet stored a bit of information. Core memory was reliable, relatively fast, and, unlike earlier forms of memory, it was non-volatile. It retained data even when the power was off. This became the standard form of computer memory throughout the 1950s and 1960s. It allowed computers to store larger programs and data sets in a way that was both stable and accessible. Without core memory, early computers would have been far less useful. Level 30. Mini-computers, DECP-DP series. By the 1960s, mainframes were powerful but prohibitively expensive. Then came mini-computers. Digital Equipment Corporation introduced the PDP series, especially the PDP-8 in 1965. It cost a fraction of a mainframe, making computing accessible to smaller businesses, laboratories, and universities. The PDPs were small enough to fit in a single cabinet and could be programmed interactively, making them more user-friendly. They played a huge role in research and education, training the next generation of programmers and engineers. Many innovations in software and operating systems, including Unix, first appeared on mini-computers. They bridged the gap between massive mainframes and the coming age of personal computing. Level 31. Time sharing and remote terminals. In the 1960s, computers were still scarce and expensive, so researchers developed time sharing. Instead of one person monopolizing a machine, multiple users connected through terminals, each getting a slice of the computer's processing time. To the user, it felt like they had their own computer, even though dozens were sharing it. Universities used this model to give students and researchers access. Terminals were simple typewriter-like devices, but they gave the illusion of personal computing before personal computers existed. This innovation democratized access to computing power and foreshadowed the client-server model that still dominates today. Level 32. Computer graphics pioneers. Early computers were designed for numbers and text, not pictures. But by the 1960s, researchers began experimenting with computer graphics. At MIT's Lincoln Laboratory, Ivan Sutherland created Sketchpad in 1963, a program that allowed users to draw directly on a screen with a light pen. This was groundbreaking. Sketchpad introduced the idea of graphical user interfaces and object manipulation decades before commercial systems like Windows or Mac. Flight simulators, video games, and CAD systems all trace their roots back to these experiments. For the first time, computers weren't just calculators. They could create and manipulate images. Level 33. Integrated circuits. As computers grew more complex, wiring thousands of individual transistors became a nightmare. The solution was the integrated circuit, or IC, invented in 1958 by Jack Kilby at Texas Instruments and independently by Robert Noyce at Fairchild Semiconductor. An IC combined multiple transistors, resistors, and capacitors onto a single silicon chip. This allowed for smaller, faster, and cheaper computers. The invention fueled Moore's law, the observation that the number of transistors on a chip doubles roughly every 2 years. Integrated circuits made possible the exponential growth of computing power, shrinking room-sized machines into devices that could eventually fit on a desk. Level 34, the Apollo Guidance Computer, one of the most famous early applications of integrated circuits, was the Apollo Guidance Computer, developed in the 1960s for NASA's moon missions. This computer, about the size of a briefcase, had just 36 kilobytes of memory and a clock speed under 1 megahertz. Yet it guided astronauts to the moon and back with incredible reliability. Astronauts interacted with it using a numeric keypad and simple display. The Apollo missions proved that digital computers could be trusted in life or death situations. It also marked the first major government investment in integrated circuits, helping push the semiconductor industry forward. Level 35. ARPANET beginnings. In 1969, the US Department of Defense funded the ARPANET, the first packet switching network and the direct ancestor of the Internet. Instead of sending information as a continuous stream, data was broken into packets, transmitted across different routes, and reassembled at the destination. The first successful message was sent between UCLA and Stanford on October 29, 1969. The system crashed after only 2 letters, but it worked. ARPANET connected universities and research labs, allowing them to share data and resources. The project demonstrated that networks of computers could collaborate, sparking the digital communication revolution. Level 36, the invention of the mouse. In 1964, Douglas Engelbart at Stanford Research Institute invented the computer mouse. It was a small wooden block with wheels that translated movement into screen coordinates. Engelbart demonstrated it in 1968 during the mother of all demos, showing not only the mouse but also hypertext, video conferencing, and collaborative editing. At the time, most people didn't see the mouse as necessary. Computers were still primarily controlled with keyboards and punch cards, but the mouse would eventually become the primary input device for personal computers, changing how humans interact with machines. Level 37, Xerox PARC and the graphical user interface. In the 1970s, Xerox's Palo Alto Research Center, or PARC, became the birthplace of many modern computing concepts. Researchers there developed the graphical user interface, or GUI, which replaced text commands with windows, icons, and menus. They also invented Ethernet networking and the laser printer. The Xerox Alto, built in 1973, was the first computer to combine these ideas, but it was never sold commercially. Later, companies like Apple and Microsoft borrowed heavily from Parker's innovations. The GUI transformed computing from something only specialists could use to something accessible to ordinary people. Level 38. Microprocessors. Intel 4004. In 1971, Intel released the 4004, the first commercially available microprocessor. Unlike earlier processors built from many chips, the 4004 packed all the central processing unit functions onto a single chip. It was originally designed for calculators, but soon found wider use. The microprocessor made it possible to build smaller, cheaper, and more powerful computers. Within a decade, microprocessors were at the heart of personal computers, video game consoles, and industrial machines. This invention marked the transition from computers as massive, custom-built systems to flexible machines that could be mass-produced. Level 39. The Altair 8800 and the birth of personal computers. In 1975, the Altair 8800 was released as a kit that hobbyists could assemble at home. It used the Intel 8080 microprocessor and had switches on the front panel to enter data in binary. It was primitive, but it sparked enormous interest. A young Bill Gates and Paul Allen wrote a version of BASIC for the Altair, founding Microsoft. Steve Wozniak and Steve Jobs were inspired to build the Apple I soon after. The Altair showed that computers didn't have to be locked in universities or corporations. Ordinary people could own one, starting the personal computing revolution. Level 40, Apple, Microsoft, and the PC revolution. By the late 1970s and early 1980s, personal computers went mainstream. Apple released the Apple II, one of the first successful mass-market PCs. It came with color graphics and a keyboard, making it accessible to schools and homes. IBM entered the market in 1981 with the IBM PC, which became the industry standard. Microsoft supplied the operating system, MS-DOS, cementing its role in software. This era marked the birth of the PC industry, with millions of people buying computers for work, education, and eventually gaming. The foundations of the modern tech giants were laid during this revolution. Level 41, Commodore, Atari, and the home computing wave. In the late 1970s and early 1980s, computers began showing up in living rooms. Companies like Commodore and Atari produced affordable machines for everyday people. The Commodore 64, released in 1982, became one of the best-selling computers of all time. It offered color graphics and sound that made it ideal for both learning and gaming. Atari's 8-bit line of computers also gained popularity, especially for games and basic productivity. Kids could learn to code in BASIC right in their bedrooms, while parents balanced budgets or played games like Pac-Man. This wave of affordable home computers planted the idea that computing wasn't just for businesses or schools. It could be personal and fun. Level 42, MS-DOS and command line dominance. When IBM released its personal computer in 1981, it needed an operating system. Microsoft, a small company at the time, supplied MS-DOS. This system was entirely text-based. Users typed commands to open programs, move files, or perform tasks. For many, it was their first encounter with computing, and while powerful, it was not friendly. Mistyped commands led to errors, and there was no visual feedback. Despite these limitations, MS-DOS became the standard for business and personal PCs through the 1980s. It solidified Microsoft's role in computing and defined how millions of users interacted with their machines for nearly a decade. Level 43, Macintosh and the desktop publishing revolution. In 1984, Apple introduced the Macintosh. Unlike earlier Apple computers, the Macintosh came with a graphical user interface and a mouse, concepts borrowed from Xerox PARC. What set it apart was accessibility. Icons, menus, and windows replaced the cryptic commands of DOS. With its bundled software like MacPaint and MacWrite, it became especially popular in creative fields. The introduction of the LaserWriter printer, combined with software like PageMaker, sparked the desktop publishing revolution. Suddenly, small businesses and individuals could produce professional quality newsletters, brochures, and books. The Macintosh proved that design, usability, and creativity could drive computing adoption just as much as raw power. Level 44. Windows graphical dominance. Microsoft responded to Apple with Windows. The first versions in the mid-1980s were clunky, but by Windows 3.0 in 1990, the system had matured into a usable graphical environment. It sat on top of MS-DOS, but it gave users windows, icons, and menus similar to the Macintosh. Because it ran on IBM PCS and their clones, Windows quickly dominated the market. Businesses adopted it en masse, and software developers focused on Windows-compatible programs. By the mid-1990s, Windows had become the default operating system worldwide. This cemented Microsoft's dominance and brought graphical computing to hundreds of millions of people. Level 45. Word processors and spreadsheets. One of the biggest reasons people bought computers in the 1980s and 1990s was productivity software. Word processors replaced typewriters, allowing users to edit text, move paragraphs, and print polished documents. Programs like WordPerfect and later Microsoft Word became staples in offices. Spreadsheets, pioneered by VisiCalc and then dominated by Lotus 1-2-3 and Microsoft Excel, revolutionized business planning. A task that once required accountants with ledgers could now be done by anyone with a PC. Budgeting, forecasting, and financial modeling became faster and more accurate. These applications turned computers from curiosities into essential business tools. Level 46. Gaming evolution, Doom and LAN parties. While productivity drove business adoption, games fueled passion. The 1980s brought titles like King's Quest and SimCity, but the 1990s saw a leap with games like Doom. Released in 1993, Doom popularized the first-person shooter genre and introduced the concept of networked multiplayer. Players could connect their computers in local area networks, or LANs, and battle each other in real time. These LAN parties became cultural phenomena among gamers. Games pushed the limits of graphics and sound hardware, forcing innovation that spilled over into other areas of computing. For many young people, gaming was their gateway into the world of PC. Level 47. Early portable computers, luggables to laptops. The dream of taking a computer anywhere began in the early 1980s with so-called luggables. Machines like the Osborne one weighed over 20 pounds, but had a small screen and could be carried like a suitcase. As technology advanced, true laptops emerged. By the late 1980s, Toshiba, IBM, and Apple offered battery-powered machines with folding screens. Business travelers could now work on spreadsheets and documents on airplanes or in hotels. Although expensive and limited in power, these machines hinted at the future of mobile computing. The idea that a computer didn't have to stay on a desk was beginning to take hold. Level 48. The World Wide Web and Tim Berners-Lee. In 1989, Tim Berners-Lee, a researcher at CERN, proposed a system for sharing information over the internet using hypertext. By 1991, the first website was live. This system became the World Wide Web. Unlike earlier internet services like email or FTP, the web was visual and interconnected. Users could click links to jump from one page to another. At first, it was used mainly by scientists, but it quickly spread to universities and then the public. The web transformed the internet from a technical network into a global medium of communication, laying the foundation for the modern digital world. Level 49. Netscape, browsers, and the dot-com boom. To use the web, people needed browsers. In 1993, Mosaic made the web accessible with images and links in one window. Its successor, Netscape Navigator, dominated the mid-1990s. With an easy interface, anyone could browse websites, fueling explosive growth. This era sparked the dot-com boom as companies rushed to build websites and online businesses. Startups promised to revolutionize shopping, news, and communication. Investors poured billions into the web economy. While many companies failed when the bubble burst around 2000, the infrastructure and culture of the web remained. Browsers became the new front door to computing. Level 50, search engines, Alta Vista to Google. As the web exploded, finding information became a challenge. Early directories like Yahoo tried to organize websites manually. Then came search engines. Alta Vista, launched in 1995, allowed users to type in queries and scan millions of pages. But it was Google, founded in 1998, that solved the problem with PageRank, an algorithm that ranked sites by relevance and links. Google quickly outperformed competitors, becoming the dominant search engine. For the first time, the entire world's information was accessible within seconds. Search became the gateway to knowledge, and Google became synonymous with the web itself. Level 51. Email and instant messaging. By the 1990s, the internet wasn't just for browsing websites. Email had become the killer application, letting people send messages around the world instantly. Unlike letters, which took days, or faxes, which required machines, email was fast, cheap, and easy. Businesses adopted it for internal communication, and soon it became a global standard. At the same time, instant messaging appeared. Services like ICQ, AIM, and MSN Messenger let people chat in real time. Teenagers spent hours online inventing new forms of communication with abbreviations and emoticons. Together, email and instant messaging redefined how people interacted across distance. Level 52. Mobile phones gaining digital features. In the 1990s, mobile phones shifted from luxury items to everyday tools. Early models were heavy and only made calls, but as networks improved, phones gained new features. Text messaging, or SMS, became a global phenomenon. In countries like Finland, teenagers turned texting into a new social language. Later, phones added calendars, simple games like Snake, and even rudimentary internet access. These changes blurred the line between phones and computers. They showed that portable, always connected devices could become central to people's lives, foreshadowing the smartphone revolution to come. Level 53. The open source revolution, Linux and Apache. While commercial software dominated the 1990s, a counter-movement grew around open source. In 1991, Linus Torvalds released Linux, a free operating system kernel that anyone could modify. Developers around the world contributed, building a powerful and flexible system. At the same time, the Apache web server became the backbone of the growing internet, also developed collaboratively and given away freely. Open source proved that communities could build software as robust as commercial offerings. Today, much of the internet and even smartphones run on Linux. The movement changed not only technology, but also the culture of computing, emphasizing collaboration and transparency. Level 54. Wi-Fi adoption. Computers had long been tied to desks with cables. That changed with Wi-Fi. Developed in the late 1990s, Wi-Fi allowed devices to connect wirelessly to local networks. At first, it was slow and expensive, but adoption grew quickly as laptops became more common. By the early 2000s, coffee shops, airports, and universities offered Wi-Fi hotspots. People could browse the web or check email without being chained to a wall. This mobility transformed how people thought about computing. No longer fixed to one place, computers became companions in daily life, paving the way for a fully mobile internet. Level 55. The beginnings of cloud computing. In the late 1990s and early 2000s, companies started experimenting with hosting applications and data on remote servers, accessible over the internet. Instead of running software on a local machine, users could log in through a browser. Salesforce, launched in 1999, was one of the first major examples offering customer relationship software entirely online. Amazon later expanded the concept with Amazon Web Services, renting out computing power and storage. Cloud computing shifted the model from owning infrastructure to paying for services. It allowed businesses to scale quickly and gave ordinary users access to powerful tools without expensive hardware. Level 56. First wave of social media, Friendster and MySpace. In the early 2000s, social media emerged. Friendster, launched in 2002, let people create profiles and connect with friends online. It was quickly followed by MySpace, which added customization, music sharing, and a vibrant youth culture. For the first time, millions of people were creating digital identities, interacting and building networks in a public space. Social media turned the internet from a library of information into a social hub. It changed how people met, shared, and expressed themselves, setting the stage for even larger platforms to dominate later in the decade. Level 57. YouTube, Facebook, and global platforms. In 2005, YouTube was launched, allowing anyone to upload and share videos. Suddenly, individuals could broadcast to the world. Viral videos and new creators emerged, reshaping media. Around the same time, Facebook, originally limited to college students, opened to the public in 2006. It quickly grew into the dominant social network, connecting billions of people. These platforms turned users into both consumers and creators of content. Traditional media struggled to compete with the speed and scale of user-generated material. Social networks and video sharing redefined communication, entertainment, and even politics. Level 58. The iPhone and the smartphone era. In 2007, Apple unveiled the iPhone. Unlike earlier smartphones, which were clunky and business-focused, the iPhone combined a phone, an iPod, and an internet device in one sleek touchscreen package. Its intuitive design and powerful hardware set a new standard. Competitors soon followed with Android devices, creating a global smartphone market. Within a few years, billions of people had pocket-sized computers with access to the web, apps, and cameras. The iPhone didn't just launch a product, it launched an era where mobile computing became central to modern life. Level 59. App stores and mobile-first computing. The iPhone's real breakthrough came in 2008 with the launch of the App Store. Suddenly, developers could distribute software directly to millions of users. Apps transformed phones into platforms for everything: banking, gaming, navigation, and social networking. Mobile-first companies like Instagram, Uber, and WhatsApp built entire businesses around apps. People began spending more time on their phones than on desktop computers. Mobile computing became the default, especially in regions where smartphones were cheaper and more accessible than PCs. The App Store model redefined software distribution and reshaped the global economy. Level 60. Big data as a concept. By the late 2000s, the explosion of digital activity created massive amounts of data. Every click, search, purchase, and social media post generated information. Traditional databases couldn't keep up. The term big data emerged to describe datasets too large and complex for conventional tools. New systems like Hadoop and NoSQL databases were developed to process this information. Companies realized they could analyze data to predict customer behavior, optimize logistics, and even influence elections. Big data shifted the focus from just computing power to information power. Whoever controlled the data controlled the future. Level 61. voice assistants Siri and Alexa. In 2011, Apple introduced Siri on the iPhone 4S. For the first time, millions of people could talk to their phones and get responses. Siri used speech recognition, natural language processing, and internet access to answer questions, set reminders, and perform tasks. It was imperfect, often mishearing or misunderstanding, but it represented a leap in human-computer interaction. A few years later, Amazon released Alexa in its Echo smart speakers. Alexa moved voice assistants into the home, controlling music, lights, and appliances. Voice assistants normalized the idea of speaking to machines, setting the stage for conversational AI. Level 62. Machine learning resurgence. Although machine learning techniques had existed since the 1950s, they often underperformed because of limited data and weak hardware. In the 2000s, two things changed. Massive datasets became available thanks to the internet, and powerful GPUs could handle the math behind neural networks. Suddenly, machine learning systems outperformed traditional approaches in fields like image recognition and speech processing. Instead of programming rules by hand, developers fed data to algorithms that learned patterns. This shift brought breakthroughs in everything from spam filters to medical diagnosis. Machine learning became the core of modern artificial intelligence. Level 63. GPUs driving neural networks graphics processing units, or GPUs, were designed for rendering video games. But researchers realized their architecture, thousands of small parallel processors, was perfect for training neural networks. Tasks that once took weeks on CPUs could be completed in days or even hours with GPUs. Companies like NVIDIA leaned into this trend, releasing specialized hardware for deep learning. The GPU revolution supercharged AI research, enabling complex models with millions or billions of parameters. This hardware shift turned neural networks from academic curiosities into practical world-changing systems. Level 64. Google Translate and natural language processing language has always been one of the hardest challenges for computers. Early translation systems were clumsy and literal. In 2006, Google Translate launched using statistical methods, drawing on vast bilingual text databases. Results were far from perfect, but they improved quickly with scale. By 2016, Google switched to neural machine translation, which used deep learning to capture context and nuance. Suddenly, translations became smoother and more natural. Millions of people around the world could communicate across languages with their phones. Natural language processing had matured from rigid rule-based systems into adaptive, learning-driven models. Level 65. Autonomous vehicles. DARPA challenged Tesla. In 2004, the US Defense Advanced Research Projects Agency, or DARPA, held a challenge. Build a vehicle that could drive itself across the desert. Early attempts failed spectacularly, but by 2005, teams succeeded, proving the concept. These competitions launched a new wave of research into self-driving cars. Companies like Google, later Waymo, invested heavily, and Tesla pushed the technology into consumer vehicles with its autopilot system. While fully autonomous cars remain rare, today's vehicles can park themselves, maintain lanes, and avoid collisions. The dream of machines that navigate the physical world is no longer science fiction. Level 66. DeepMind and AlphaGo milestone. In 2016, DeepMind, a company owned by Google, shocked the world when its program AlphaGo defeated Lee Sedol, one of the best players of the ancient board game Go. Go was considered too complex for computers, with more possible board states than atoms in the universe. Traditional brute force approaches were useless. AlphaGo used deep neural networks and reinforcement learning to master strategies beyond human intuition. When it played, it produced moves that stunned experts for their creativity. This victory marked a turning point, showing that AI could not only match humans, but also innovate in domains once thought uniquely human. Level 67. Cloud AI platforms AWS, Google Cloud, Azure. As AI advanced, companies needed infrastructure to support it. Cloud platforms like Amazon Web Services, Google Cloud, and Microsoft Azure began offering AI tools on demand. Instead of buying expensive hardware, developers could rent processing power, pre-trained models, and data storage over the internet. This democratized AI, allowing startups and researchers to build advanced applications without massive budgets. Cloud AI services now power chatbots, recommendation engines, medical analysis, and countless other systems. The cloud shifted AI from elite labs into everyday businesses, accelerating adoption worldwide. Level 68. Computer vision in smartphones, Face ID, and AR apps. By the late 2010s, smartphones had become the most powerful computers most people owned, and computer vision turned them into advanced sensors. Apple's Face ID used infrared cameras and neural networks to map and recognize a person's face securely. Augmented reality apps placed digital objects into real-world environments through the phone's camera, blending physical and digital experiences. These capabilities, once the domain of expensive labs, now fit in a pocket. From Snapchat filters to medical imaging, computer vision in consumer devices showed how AI could integrate seamlessly into daily life. Level 69. Quantum computing experiments. While classical computers rely on bits that are either 0 or 1, quantum computers use qubits, which can be in superpositions of both. This allows them to perform certain calculations far more efficiently. In the 2010s, companies like IBM, Google, and D-Wave built experimental quantum computers. Google announced in 2019 that its system had achieved quantum supremacy, solving a problem in minutes that would take classical supercomputers thousands of years. Although practical quantum computing is still in its infancy, the field promises breakthroughs in cryptography, optimization, and drug discovery. It represents the next frontier of computing power. Level 70. AI in healthcare and biotech. One of the most promising applications of AI has been in medicine. Algorithms trained on millions of medical images can spot cancers as accurately as human doctors. Systems analyze genetic data to suggest personalized treatments. In drug discovery, AI can predict how molecules will behave, speeding up processes that once took years. During the COVID-19 pandemic, AI models helped track outbreaks and analyze vaccines. Healthcare has always depended on data, and AI makes it possible to process that data at unprecedented scale and speed. The potential to save lives and cut costs makes this one of the most important frontiers for computing. Level 71. Crypto, blockchain, and decentralized computing. In 2009, Bitcoin was introduced by the mysterious figure known as Satoshi Nakamoto. At its core was the blockchain, a distributed ledger that recorded transactions across a decentralized network of computers. No single authority controlled it, and every participant could verify the records. Blockchain technology solved the problem of trust without central oversight. While Bitcoin focused on digital money, the underlying concept opened the door to decentralized applications in finance, supply chains, and even voting systems. Blockchain was more than cryptocurrency. It was a new model of computing where consensus and transparency replaced central control. Level 72. The Internet of Things, smart homes and wearables. As computers shrank and wireless networks spread, devices other than PCs and phones began connecting to the internet. Refrigerators, thermostats, security cameras, and watches became smart wearables like Fitbit, and Apple Watch collected health data, while smart speakers controlled household functions. This Internet of Things, or IoT, created networks of billions of devices generating constant streams of data. Cities began adopting sensors for traffic and pollution monitoring. Factories integrated IoT for automation and predictive maintenance. The idea of computing expanded from discrete devices to an ecosystem of interconnected, always-on machines woven into daily life. Level 73. Edge computing. As billions of IoT devices came online, sending all their data to distant cloud servers became inefficient. Edge computing emerged as a solution. Instead of processing data only in centralized data centers, edge computing pushes processing closer to where data is generated, at the edge of the network. For example, a self-driving car can't wait for cloud servers to decide when to brake. It must process sensor data instantly on board. Similarly, smart cameras can analyze footage locally before sending summaries to the cloud. Edge computing reduced latency, improved privacy, and allowed real-time decision-making. It was a shift in where and how computing happens. Level 74. Natural language models, GPT-2 and GPT-3. In 2019, OpenAI released GPT-2, a large-scale language model capable of generating coherent paragraphs of text from simple prompts. The following year, GPT-3 expanded this capability with 175 billion parameters, producing text so human-like it startled both researchers and the public. These models didn't just parrot phrases, they learned patterns of language, enabling them to write essays, generate code, answer questions, and even hold conversations. Natural language models represented a leap in AI's ability to understand and generate human-like communication. They shifted computing from rigid commands to flexible conversational interaction. Level 75. Large-scale data centers and energy questions. Behind the digital revolution stood enormous data centers, the factories of the information age. Companies like Google, Amazon, and Microsoft built facilities the size of football fields, packed with servers, cooling systems, and power infrastructure. These centers powered search engines, cloud services, social media, and AI training. But their growth raised questions about sustainability. Data centers consumed massive amounts of electricity and water, often rivaling small cities. Companies invested in renewable energy and efficiency improvements, but the tension between limitless digital growth and physical resource constraints became a central issue for the future of computing. Level 76. Robotics and soft AI robotics had long been a dream of science fiction, but by the 2010s, advances in AI and sensors brought it closer to reality. Industrial robots already dominated factories, assembling cars and electronics with precision. Newer robots entered homes like the Roomba vacuum cleaner. More advanced systems, such as Boston Dynamics robots, demonstrated running, jumping, and even dancing. At the same time, AI-powered soft robots emerged in fields like healthcare, assisting with surgery or elder care. Robotics showed the physical side of AI, where intelligence wasn't just about information, but about interacting with the real world. Level 77. Neural architecture search and AutoML. As AI models grew in size and complexity, designing their architectures became a specialized art. Neural architecture search and automated machine learning, or AUML, shifted some of that work to the machines themselves. Instead of engineers handcrafting every detail, algorithms could explore and optimize architectures automatically. This made powerful AI more accessible, lowering barriers for smaller teams and organizations. AutoML represented a meta-level of computing, machines not only performing tasks, but also designing better ways to perform them. It was the automation of intelligence creation itself. Level 78. Generative AI in art, music, and text. By the early 2020s, AI moved from analysis to creation. Tools like DALL-E, Midjourney, and Stable Diffusion could generate images from text prompts. Musicians experimented with AI-composed songs. Writers used language models to draft stories, scripts, and poetry. Generative AI blurred the line between human and machine creativity. Some saw it as a tool for inspiration, while others feared it would replace artists. Regardless, it showed that computation was no longer limited to solving problems. It could participate in culture, aesthetics, and expression. For the first time, machines became collaborators in the creative process. Level 79. Ethical dilemmas in AI. As AI systems spread, so did concerns. Facial recognition raised issues of privacy and surveillance. Algorithms in hiring or policing risked reinforcing biases hidden in their training data. Deepfakes created convincing fake videos threatening trust in media. Autonomous weapons sparked debates about machines making life or death decisions. Governments, companies, and ethicists wrestled with how to regulate and guide AI development responsibly. These dilemmas weren't just technical, they were societal, asking humanity to decide how much power to give intelligent systems and how to align them with human values. Level 80. AI as a co-worker. By the mid-2020s, AI had moved into the workplace. Chatbots handled customer service. AI tools drafted legal documents, analyzed contracts, and wrote code. Systems supported doctors by suggesting diagnoses or treatment plans. Rather than replacing all workers, AI became a co-worker, handling repetitive tasks while humans focused on judgment and creativity. This shift sparked debates about productivity, job security, and the meaning of work itself. For many industries, the human-AI partnership became the new normal. Computing was no longer just a tool, it was a collaborator. Level 81. Chatbots becoming companions. Chatbots began as simple customer service tools, answering basic questions with pre-programmed replies. By the 2020s, they evolved into far more capable conversational agents powered by large language models. People started turning to them not only for information, but also for companionship. Some used them for practicing languages, others for emotional support, and still others as virtual friends. While they cannot truly feel or empathize, their ability to hold convincing conversations blurred the line between tool and companion. This raised new questions. If people bond with chatbots, what does that mean for human relationships and social behavior? Level 82. AI in scientific research acceleration. AI became a powerful partner in science. Algorithms sifted through massive datasets in physics, biology, and astronomy to spot patterns humans missed. In 2020, DeepMind's AlphaFold solved a 50-year-old challenge by predicting the three-dimensional structure of proteins with remarkable accuracy. This breakthrough opened doors in drug discovery and molecular biology. In astronomy, AI helped detect exoplanets by analyzing subtle changes in starlight. Scientists began relying on AI to generate hypotheses, design experiments, and even write parts of research papers. With AI accelerating discovery, the pace of science itself began to change. Level 83. Human-AI collaboration in creativity and beyond science. AI became a creative partner. Writers used AI to brainstorm story ideas or draft passages. Musicians employed it to suggest melodies or harmonies. Architects explored AI-generated designs that combined function with striking aesthetics. Rather than replacing artists, many found that AI expanded their creative possibilities, offering perspectives they might not have considered. This collaboration echoed Ada Lovelace's prediction nearly 2 centuries earlier, that machines could manipulate symbols to create art and music. Creativity, once thought purely human, became a shared space between people and machines. Level 84. Explainable AI and trust. As AI systems became more powerful, a problem emerged. Many operated as black boxes. They produced results without clear explanations of how those results were reached. This made trust difficult, especially in critical areas like medicine, finance, and law. Explainable AI, or XAI, arose to address this. Researchers developed methods to make AI decisions interpretable, highlighting which data influenced outcomes. For example, a medical AI could show which features of an X-ray led to a cancer diagnosis. Explainability wasn't just a technical goal, it was essential for building public trust and ensuring accountability in intelligent systems. Level 85. Augmented reality and mixed reality blending with AI. Augmented reality, or AR, overlays digital information onto the physical world. Mixed reality goes further, blending the two seamlessly. When combined with AI, these technologies became even more powerful. Smart glasses could recognize objects and provide real-time translations, navigation, or instructions. In education, students could explore virtual reconstructions of historical sites while walking through their classrooms. In medicine, surgeons used AR overlays to guide procedures with precision. By linking vision, AI, and interactive displays, augmented and mixed reality promised to change how people experienced both work and play. Level 86. AI in global governance and policy. As AI shaped economies, communication, and even security, governments had to respond. Nations debated regulations on data privacy, surveillance, and autonomous systems. The European Union introduced strict rules on how AI could be developed and used, emphasizing ethics and transparency. At the same time, AI became a geopolitical issue. Countries competed to lead in AI research, seeing it as a driver of military and economic power. International bodies began discussing treaties to manage AI responsibly, similar to past agreements on nuclear technology. Computing had moved beyond labs and corporations into the realm of global governance. Level 87. Quantum supremacy milestones. Quantum computing, once theoretical, began achieving real milestones. In 2019, Google announced it had performed a calculation in 200 seconds that would take classical supercomputers thousands of years. While the problem itself had little practical use, the demonstration was historic. Other companies and labs raced to build more stable qubits, reduce error rates, and scale systems beyond prototypes. Quantum supremacy didn't mean replacing classical computers. It meant entering a new paradigm where certain problems, cryptography, materials science, optimization, could one day be solved in ways impossible with today's machines. Level 88. Neural implants and brain-computer interfaces. Researchers began exploring direct links between the human brain and computers. Early brain-computer interfaces helped paralyzed patients move robotic limbs or type messages by thought. Companies like Neuralink promised even more ambitious applications, restoring vision, enhancing memory, or enabling direct communication between people. These technologies remained experimental but pointed toward a future where biological and digital systems could merge. Neural implants raised profound questions about identity, privacy, and autonomy. If a machine can read or even influence your thoughts, where does human control end and computer control begin? Level 89. AI-designed hardware. Traditionally, humans designed the chips and circuits that powered computers. But as systems grew more complex, AI began taking on the role of hardware designer. Machine learning algorithms optimized chip layouts, improving efficiency and speed in ways human engineers might overlook. Google used AI to design its tensor processing units, specialized chips for deep learning. This created a feedback loop, AI helping to build better AI. When machines design the very hardware they run on, the pace of improvement accelerates. The boundary between creator and tool started to blur even further. Level 90. Artificial General Intelligence debates. By this stage, public debate about artificial general intelligence, or AGI, had grown louder. Unlike narrow AI systems which excel at specific tasks, AGI would match or exceed human intelligence across domains. Some experts argued it was decades away, while others believed it could emerge unexpectedly as models scaled. Optimists saw AGI as a path to solving humanity's greatest problems. Pessimists feared loss of control, economic disruption, or existential risk. Governments, companies, and researchers argued over how to prepare. The question was no longer whether machines could think, but what would happen when they did. Level 91. Climate-scale simulations with AI. One of the most urgent uses of advanced computing has been modeling Earth's climate. Traditional models struggled with the sheer complexity of atmospheric, oceanic, and ecological systems. With AI, researchers began running climate simulations at unprecedented scale and detail. These models predicted extreme weather events, rising sea levels, and long-term environmental changes with greater accuracy. Governments and organizations used them to plan infrastructure, agriculture, and disaster response. Computing at this level wasn't about convenience, it was about survival. The planet itself became a system to be computed. Level 92. AI in warfare and defense militaries adopted AI for surveillance, logistics, and strategy. Drones used machine vision to identify targets. Algorithms optimized supply chains and battlefield communication. More controversially, autonomous weapons capable of making lethal decisions without human oversight entered development. Some argued they reduced risks to soldiers, while others warned of a destabilizing arms race. The debate paralleled earlier fears about nuclear weapons. Once again, computing was not just shaping economies and culture, it was altering global security. The future of warfare became inseparable from the future of AI. Level 93. Fully autonomous vehicles. After years of testing, self-driving cars, trucks, and drones reached maturity. Urban areas began adopting fleets of autonomous taxis and delivery robots. Highways saw long-haul trucks running day and night without human drivers. These systems reduced accidents, lowered costs, and transformed industries from logistics to insurance. But they also disrupted millions of jobs. Society faced questions about retraining workers, redesigning cities, and handling edge cases where machines still struggled. The dream of self-driving machines finally arrived, but its consequences rippled far beyond transportation. Level 94. Personalized AI tutors and education systems. Education shifted with AI tutors capable of adapting to each student's learning style. Instead of one-size-fits-all classrooms, children interacted with systems that explained concepts at their pace, offered tailored exercises, and provided instant feedback. For adults, AI tutors supported lifelong learning, reskilling workers in changing industries, while human teachers remained essential for mentorship and social development. AI amplified their reach. Education became more accessible globally, with personalized learning delivered through inexpensive devices. Computing reshaped not just how we work, but how we learn. Level 95. AI in law and governance legal systems, once reliant on armies of clerks and lawyers, integrated AI to handle contracts, case law, and evidence analysis. Systems drafted legal documents, predicted case outcomes, and even advised judges. Governments experimented with AI to model policy impacts before implementation. While efficiency improved, critics warned about bias, transparency, and accountability. Could a defendant trust a system if they didn't understand how it reached its conclusion? The law, once the slowest changing of human institutions, found itself reshaped by algorithms. Governance entered the age of computation. Level 96. Synthetic biology and computational design of life computers began designing not just machines, but living organisms. With advanced modeling, scientists engineered synthetic DNA sequences to create bacteria that produced medicines, fuels, or biodegradable plastics. AI analyzed genetic data to propose edits, guiding CRISPR and other tools. Entire metabolic pathways were simulated before being built in labs. Biology became programmable, with DNA treated as code. The line between digital and biological blurred, raising both enormous potential and ethical dilemmas. Life itself entered the realm of computation. Level 97. Fully immersive virtual worlds. As computing power and graphics advanced, virtual reality matured into fully immersive experiences. People worked, studied, and socialized in persistent digital environments, often indistinguishable from physical spaces. These worlds weren't just entertainment, they hosted economies, education systems, and even governments. Combined with AI-driven characters and environments, virtual worlds became places where human and machine intelligence coexisted. Some saw them as escapes, others as extensions of reality. Computing was no longer confined to screens. It became a second world in which humanity lived. Level 98. Human-AI symbiosis. Brain-computer interfaces, wearable sensors, and AI assistants began merging into daily life. People augmented their memory, attention, and decision-making with digital partners integrated into their thoughts and actions. Instead of looking at a screen for directions, navigation unfolded directly in their minds. Workers collaborated with AI not as separate tools, but as extensions of themselves. This symbiosis blurred the boundary between human and machine. Computing was no longer external. It became part of human identity. Level 99. Artificial general intelligence emerges. After decades of speculation, artificial general intelligence arrived. Machines demonstrated reasoning, adaptability, and problem-solving across domains at or above human levels. Unlike narrow AI, AGI could learn any task, transfer knowledge, and generate original ideas. The consequences were profound. Some AGEs became partners in science, accelerating discovery beyond human pace. Others raised fears of autonomy, control, and alignment with human values. Humanity faced the central question: how to coexist with intelligence that was no longer artificial, but truly general. Level 100. The unknown frontier. From tally sticks to AGI, computing's journey was one of exponential growth. Each level built on the last, carrying humanity from counting sheep with stones to designing life and intelligence itself. The path forward remains uncertain. Will AGI become a partner in solving humanity's greatest challenges? or will it create risks beyond control? Will humans merge with machines or remain distinct? The only certainty is that computing will continue to evolve. Level 100 is not an end. It is the beginning of the next unknown frontier.